I went to this video on how to approximate learn 2. Now, we're not going to be using any calculators. We're going to, like last time, we're going to be using square root, multiplication. That's it. That's our only tools available to us. Now, what we're first going to do is we're going to find an easy but bad way to calculate learn 2. We're going to demonstrate this with a graph. We're then going to come up with an idea on how to fix this. And then in step 2, we're going to introduce the idea on how to implement this fix. We're going to create a recurrence relation, and then we're going to calculate learn 2 to high precision using this method. So I've got a desmos plot up here of learn of 1 plus x. Now, you might have already assumed that we're going to use a Taylor series of learn. Now, why does this not work so well? Well, let's see the Taylor series up to one term. Well, okay, it's kind of accurate. It gives a good representation at x equals 0. Adding that on, we get a better representation, but it's still not great. Adding on another term, okay, gets better. But what you'll notice is as x gets further and further away from 0, we're going to get a lot more deviation from this line. So ideally what we want to do is we want to get closer to the point 0. Now, a lot of people will calculate learn 2 as replacing x with 1. So learn 2 as learn of 1 plus 1, replace x as 1 in this Taylor series. That'll give us a good approximation. But what we see is there's at x equals 1, which is down here, we're going to get a big difference, even up to 3 terms. Even up to 10 terms, we're going to get a big difference. Remember, 1 is here. This is what, 0.69. This here is 0.664. So we haven't even got 2 decimal places of accuracy. So we're going to see a way of trying to get x to be closer to this 0. We did this when we were calculating pi. We found a trick with arctan. We're going to try to find a similar trick with learn of 1 plus x. So my idea for this is, as x gets smaller, which is what we want x to be much smaller, we get that learn gets much smaller. Now, it's quite hard to make x smaller. It's quite hard to manipulate the inside of this learn of 1 plus x to make x smaller because of the 1. The 1's kind of in our way. So what I want to do is I want to actually make the learn part smaller. So I want to calculate a smaller value of learn, but I still want it to be equivalent to learn 2. So this is my idea on the whiteboard. So I want to write learn of 1 plus xn to be the same as 2 learn of 1 plus xn plus 1. So when I go to the next term, I want the learn part to be like this. Now you might, with like an own idea that you might want to explore, you could change this to say a or to something like that, and maybe increase the size of the polynomial that we're going to get out. Now, the reason I've taken 2 is because we're going to get quadratic, a lot easier to solve than other cubics. So let's have a go at actually solving this. Now, ideally I need to get rid of the learns for my recurrence relation. I don't want to have to calculate learn in my recurrence because we're kind of assuming we don't know what the learn function does. So I need to bring the 2 inside. So this is the same as learn of 1 plus xn plus 1 squared. Now I can get rid of the learns. We get 1 plus xn equals 1 plus xn plus 1 squared. And if you saw my video on calculating pi, we did a similar trick where we took this to be a quadratic in xn plus 1. So expanding this all out and bringing the xn and the 1 over, we get xn plus 1 squared plus 2xn plus 1. Now the 1's will cancel and we're just going to be left with a minus xn. Like this. So xn plus 1, solving this quadratic, is going to be minus 2 plus or minus square root of b squared minus 4ac. Now a is 1, c is minus xn, so we're going to be plussing 4xn over 2. Next, we can simplify this to be minus 1 plus square root of 1 plus xn. Now I've chosen to take the plus because we want to make sure what's inside our learn is positive. Notice, if I was to replace xn plus 1 in here, the 1 will cancel. We don't want minus xn or minus square root left over. We want a positive square root left over, which will be a lot nicer for us. So we've now got ourselves a recurrence relation. Now we had that x0 is going to be 1. So x1 is going to be minus 1 plus square root of 2. x2 is going to be 0.189207115. x3 is going to be 0.0905077327, whatever. We're getting quite a lot of small numbers now. And while decreasing this more, we get x4 as 0.442737, blah, blah, blah. I'm going to do a few more clicks. Let's get it down to x7, which is 0.0054299011113, which is a very small number. Now, this is all well and good. We now actually want to go and calculate learn 2 using this formula. So we have that learn of 1 plus x0 is equal to 2 learn of 1 plus x1, which means we're going to have that it's going to be 2 to the n learn of 1 of xn. So really what we're calculating is 2 to the power of 7 times learn of 1 plus x7. So now we need to calculate learn of 1 plus x7. So to do this, we need to make use of the expansion of learn that I've got here. Now I'm only going to do it up to n equals 3. So what we're doing is we're doing 2 to the 7 times x7 over 1 minus x7 squared over 2 plus x7 cubed over 3. And well, if you calculate this is 0.693147208. And comparing this to learn 2, well, learn 2 is 0.69314471806. So it's kind of close. We get failure here, but it's pretty close considering all we've done is multiplication and a square root. Now, if you were to do more terms in the recurrence relation, we'd get more accuracy. Likewise, if we do more terms in our power series, we'll get more accuracy. I'll leave that for you guys to investigate.